Hello, my name is Ethan Weber, and in this presentation I will be discussing my work on touchless electrostatic detumbling of differentially charged spacecraft in geosynchronous Earth orbit. In GEO orbit, debris objects have been observed to be tumbling at rates of tens of degrees per second, and these high tumble rates can create significant collision and momentum transfer risks for contact-based servicing missions and debris removal missions that rely on physical capture methods. Electrostatic detumbling is a technique that bypasses these risks by touchlessly detumbling a debris object using electrostatic torques. In this method, a servicing spacecraft is equipped with charge control methods like an electron gun, and it uses this electron gun to control both the target and surfacer charging, and uses these charging to create either attractive or repulsive torques as shown on the right figure between the surfacer and the target, and these torques are used to detumble the spacecraft. Prior work on electrostatic detumbling has focused on fully conducting target spacecraft that charge to a single uniform potential. When a fully conducting charged spacecraft is in the proximity of a differently charged surfacer spacecraft, the charges in that target redistribute themselves in order to maintain a uniform voltage across all their components. And this causes the center of charge of that target to shift. And when this center of charge shifts away from the center of mass, if the vector between the center of charge of the target and the center of charge of the surfacer are not aligned with the center of mass, you get an electrostatic torque resulting from that. And in the past, prior work has used this effect with active charge control using an electron beam to control this electrostatic torque and use the electrostatic torques to detumble the spacecraft. Now, while this prior work has shown that electrostatic detumbling is a promising technique, the assumption that a target spacecraft is fully conducting is not always valid for GEO spacecraft. One of the main gaps in this research is that many legacy spacecraft are not fully conducting. And this can either be because they were not designed to be fully conducting in the first place, or because previous electrical connections have been damaged or worn down over time, resulting in electrically disconnected components. In this situation where a spacecraft is not fully conducting, electrically disconnected surfaces can charge to widely varying electrical potentials, and this enables stronger electrostatic torques to be produced, like shown in the figure on the screen. And in this figure, we see there is a repulsive force between the positively charged target panel that is disconnected from the rest of the target spacecraft. And we get that repulsive force between this positively charged panel and the positively charged surfacer. But we also get an attractive force between the negatively charged spacecraft bus and panel and that surfacer. And by having both of these different forces and basically shifting the center of charge even more using this differential charging, we can achieve stronger electrostatic torques. Now, in order to make use of these greater torques for the purposes of electrostatic detumbling, we need a way to control the differential voltage distributions on the target. In this paper, I propose the use of a broad electron beam that illuminates both the target bus as well as the disconnected panel. And this broad electron beam provides a global negative current across all of these target components. Then we use a targeted UV beam that focuses UV photons on a specific component to produce localized photoelectron emissions on those isolated components. And this results in a local positive current. And this combined allows us to create negatively charged and positively charged patches on disconnected surfaces on the target spacecraft. And this brings us to the two main questions addressed by this paper. First, what electron beam and UV illumination parameters are needed to produce meaningful differential voltage control across a target? And second, what can differential voltage control enable more efficient electrostatic detumbling than the uniform charging case shown in prior work? To address these questions, I consider a detumbling scenario with two spacecraft in GEO orbit with typical space weather conditions, a KP index of 0 and a local time of 12, meaning that the spacecraft are between the Sun and the Earth. In this scenario, the target spacecraft is a GOES-R-shaped spacecraft with an isolated solar panel, as shown in the bottom right figure, while the surfacer is a simple box-wing spacecraft. The target spacecraft starts with an initial tumble rate of 2 degrees per second, and this is a tumble around the target body 3 axis, or the axis that we see in the magnetometer boom on the figures on the right. And detumbling is considered to be achieved. The goal is to detumble down to a situation where the body angular rates are all beneath 0.05 degrees per second in each of the body axes. And as mentioned before, the main ways of controlling the charging on both the target components and the surfacer is through an electron beam and a UV light source on that surfacer spacecraft. Now, using this UV beam and the electron beam, we get 6 total voltage control modes. The first control mode is when neither the electron beam or the UV beam are turned on. And in this situation, all isolated components charge to a slightly positive potential. And this is because we chose the local time to be 12. So both the target components and the servicer are in the sunlight, and this solar photon flux creates a slight positive current due to solar photoelectrons. And in that bottom table, each of the control modes is compared to this natural charging case, with positive meaning that the potential of that component is slightly higher or more positive than what it is in this natural case, and negative being the opposite. The next control mode we consider is using an electron beam to hit both target components. And when we are illuminating both target components with the electron beam, this causes them both to absorb electrons and charge negatively, while the servicer charges positively because it's emitting electrons. Now, to get into differential charge control, we consider the case where we have an electron beam that is illuminating both targets. We also have a UV beam that is illuminating, in this case, just the target bus. And when the UV beam hits the target bus, it creates localized photoelectron emissions that charges that target bus more positively, while the target panel is still charged negatively. And in the next control mode, we have the same thing, but this time the target bus and target panel are switched. Finally, we look at the fifth and sixth control modes, which have the same UV illumination as before, but this time without the electron beam, and these simply cause the illuminated components to charge slightly more positively than the other target component in the same situation. Now, moving on to the methods. Now, returning to our two main questions, to address the first question of what beam parameters are required to produce a meaningful differential target voltage control, a charging study is performed to determine the minimum electron beam current and the UV beam power needed to produce kilovolt level voltage control. And these minimum parameters are then used to answer the second question of whether voltage control can enable more efficient electrostatic detumbling. First, the steady-state voltage distributions produced by each of those 6 control modes I mentioned before are calculated using the results of that parameter study, so using the E-beam current and the UV beam power. And then these control mode voltages are used to run differential detumbling simulations with a Lyapunov optimal voltage control mode switching method that I discuss about 2 slides from now. To perform the parameter study and control mode voltage analyses, a differential charging model is developed, and this charging model is shown in the top left. And using this model, the voltages across each electrically isolated component, so the target bus, target panel, and the servicer, are all integrated. And because we're considering a complex spacecraft geometry, we can't just use analytical values for the elastance, which is that S matrix. So instead, we use what is called the surface multisphere method, or surface multisphere model. And in this model, the spacecraft are treated as a collection of charged spheres that are distributed across the surface of the spacecraft, and that's shown in the bottom right figure. And the elastance matrix is basically built by taking the spherical elastance of each of these spheres and creating an elastance matrix from the contributions of each of these. And this improves computational efficiency compared to a full FEA approach, and is really necessary because using a full FEA approach, you'd have to integrate across all the surfaces on each spacecraft. Overall, this charging model, using both the charging differential equations and the surface multisphere model shown on screen, is used to determine the minimum electron beam and UV illumination parameters as mentioned before. And these parameters are used to calculate the steady-state voltages produced for all 6 of the control modes mentioned earlier. Using these steady-state control mode voltages, the differential electrostatic detumbling can finally be simulated, and this is done using the simulation loop shown on the left. For a quick overview, at each time step, the detumbling system determines which voltage control mode is optimal, and it does this by first figuring out what the charge is on each of the spheres in a surface multisphere model based off of the voltages found previously. And using these charged spheres, a force can be calculated between each sphere on the target spacecraft and each sphere on the servicer spacecraft, and the sum of these forces can be crossed with the distance from each sphere from the center of mass of the target, and this gives us the total torque, electrostatic torque, acting on the target. And using this method, we can figure out what the torque is produced by all 6 voltage modes at each time step. And this is then plugged into a Lyapunov control mode selection scheme, where we have an angular rate-based Lyapunov function. And taking the Lyapunov derivative, we want this derivative to be as negative as possible to have maximum detumbling stability. And we basically choose which voltage we want to use by having this argmin statement. We basically find which voltage combination minimizes the Lyapunov derivative. And this control methodology is explained in further detail in my paper if you're interested in more details. Now to get into the results of the parameter study, charging analysis, and the detumbling simulations. Starting with the electron beam parameter study, we consider the control mode where only the electron beam is turned on, and to determine the minimum parameters needed to drive both target components to a negative kilovolt level potential, we have the electron beam energy set to a value of 20 kilovolts, and this dictates the maximum potential difference between the target components and the surface or spacecraft. And using this energy, the electron beam current is varied between 0.5 to 2 milliamps. And when we look at this plot, we can see that both components are driven to a negative potential at around 1.1 milliamps. So that is the electron beam current value that we use for the rest of these studies. So using this 1.1 milliamp electron beam current, the minimum UV beam parameters are explored for both control modes where we have the electron beam on, and then the UV beam is hitting either the panel or the bus. And the panel case is shown on the left and the bus case is shown on the right. In this study, the UV beam wavelength is set to 190 nanometers, and this is simply based off of values seen in commercial off-the-shelf UV light sources. And using this wavelength, the beam power is varied. And observing these plots for both of the control modes being considered, we see that the beam power needs to be around 7 watts based off of the plot on the right in order to produce kilovolt level differential voltage control for both control modes. It is important to note that this 7 watt value is considerably higher than the powers generally seen for commercial off-the-shelf UV light sources, but this is also not a power draw that would be infeasible for the power capabilities of a GEO spacecraft, and you could likely achieve this by using multiple UV light sources, or if in the future a more powerful UV light source is developed, that could also be used. Now, using these electron beam and UV beam parameters, the steady state voltage produced by each control mode is calculated with the voltage distributions, and these are shown in the upper table. Two combinations that are kind of note are highlighted in the table, and these are when we have the electron beam on and the UV beam illuminating both the bus, or either the bus or the panel. And in these we see that we get multiple kilovolt level differential charging, showing that we are able to achieve differential charging using these beam parameters. We also see that these results match the expected trends from the change in voltage from before. That's shown in the bottom table. And that is really just showing that our expected voltages match what we're actually seeing in our analysis. Now, using these voltage values, the detumbling scenario can finally be simulated. As mentioned before, the target starts with a tumble rate of around 2 degrees per second in the body 3 axis, and detumbling is achieved when all body angular rates are less than or equal to 0.05 degrees. On this slide, the angular rate evolution of both the uniform case shown on the left and the differential case shown on the right are shown, and both simulations are run for 500 simulation hours, or approximately 3 weeks. Observing these plots, we see that the uniform charging case on the left takes around 450 hours to detumble the chosen geometry, which is the GOES-R spacecraft, while the differential charging case takes less than 300. And this is a reduction of around 150 hours, or approximately 33%, showing that differential detumbling has a lot of promise for considerably reducing electrostatic detumble times. Now, to understand why there's such an improvement, we can look at the body frame torques imparted on the target spacecraft during detumbling. When we compare the torques about the body 3 axis for both the uniform case and the differential case, we can see that the differential case can command torques nearly 1.5 times as large as the uniform case. And these enhanced detumbling torques explain why we see such an improvement in the differential charge control case. When you're able to produce larger torques, you can detumble faster. Overall, the results of this work are as follows. First, we find that for the spacecraft geometry considered and the detumbling scenario considered, a large UV beam power would be needed to produce meaningful differential charging. And while this power is larger than what's available from the commercial off-the-shelf UV light sources, it's not infeasible for the power capabilities on GEO spacecraft, and it could be achieved by using multiple light sources, or if a novel technology is developed, it could also be achieved using that. Next, the simulation results for the detumbling showed that differential voltage control can enable much greater electrostatic torques than the uniform case, and this follows what we expect from theory. When you have stronger torques, you can produce faster detumbling, and this is also what we see for the simulated detumbling scenario, where we get approximately a 33% faster detumble time. The next steps are to look at simulating additional detumbling cases, improving the differential charge modeling fidelity, and studying the effects of differential charging on detumbling when we assume a uniform charging case like in previous work. Thank you for watching. If you have any questions, feel free to reach out to me using the email address on screen. Further, you can view this publication at the link shown in the bottom on the screen. Thank you.